Hello everyone. First of all, thank you very much for the kind introduction and for the invitation to give this seminar, which I'm very happy to do. In the next 45 minutes or so, I will tell you about some of our latest work in obtaining accurate electronic and optical excitations from a certain set of methods that we developed within density functional theory, which we call screened range separated hybrid functionals. And of course, I'll explain what that actually means as I go along. So before I dive into the actual science, just to give a few words of thanks to my group. This is a recent online meeting of the group. Various funding sources that have supported our work in the last 10 years or so. And of course, I will mention specific students and also specific collaborators as I go along. Okay, so first of all, a few words about density functional theory in general. The basic idea of density functional theory is that all of the information that is in the many-body wave function, which is a very complicated object, can already be obtained from a much simpler object, and that is just the total density of the system. This is why it's called density functional theory. Now, this has many ramifications, but the most practical application of this idea is what's known as the Kohn-Sham equation after its two developers, where basically we use this idea to map the original interacting electron problem into an equivalent problem of non-interacting particles. Equivalent in what sense? Equivalent in the sense that the density that we will collect from the non-interacting particles is exactly the same as the original density. And since I already told you that all of the information is in the density, that means that we can also get the energy and other related quantities. And I'll show examples as I go along. So the bottom line is that we have a Schrödinger-like single particle equation with the usual kinetic energy term and an ionic potential, which describes the attraction of electrons to the ions. Then there's a Hartree term, which is basically the classical repulsion of electrons from each other. And all of the many-body quantum physics, which is the hard part, is embodied in another potential, which is known as the exchange correlation potential. And it's called that way because exchange really means enforcing anti-symmetrization of the wave function or enforcing Pauli's exclusion principle. And correlation means how the motion of various electrons is connected to the motion of other electrons beyond just the need to obey Pauli exclusion. So then I have this equation, and the magical thing about this equation is that it's actually exact. This is not an approximation. One can show that there is such an exchange correlation potential. It's really a functional derivative of an energy quantity known as the exchange correlation energy. That itself is a functional of the density, which is what gives the theory its name. So everything up to this point is completely exact. Only problem is that it's only exact in principle. In practice, it's almost always approximate because we don't know what this exchange correlation energy is. We know that it's a unique object, but it's a complicated and generally unknown functional of the charge density. So that means that a lot of the effort in density functional theory development is actually to find better and better approximations for how this exchange correlation energy depends on the density. The simplest and also historically the first approximation is known as the local density approximation. And that just says that, well, we don't know the solution to the general problem, but we can solve the relatively simple problem of a homogeneous electron gas once and for all. And when we do that, then we can assume crudely that even for a non-uniform system, the exchange correlation energy per particle at each point in space will be given by its appropriate value from the homogeneous electron gas. So as if I have a homogeneous electron gas with that density at that point, and then I just weigh over the different densities. Now that sounds like a very crude idea, excuse me, because clearly the real problem is very far from being uniform in density in general. So even the developers of this approximation, which are Kohn and Sham, didn't believe it would be useful. And it's not always good, as I will show you later, but sometimes it is. Here's very early work from Yin and Cohen from a little over 40 years ago already. They looked at silicon. And they calculated using this local density approximation, the energy as a function of the volume for various hypothetical structures, FCC, BCC, HCP, etc. So what they found is that the theory really predicts that the diamond structure is the most stable one, which is correct for silicon, that the volume at which the minimum is obtained is almost in perfect agreement with experiment. They also found that if you go to tighter volumes by applying pressure, then the stable phase changes to be the beta-tin one, which is again known experimentally and correct. They could also calculate transition pressure and transition volumes, and later on also phonons, and everything agreed very well with experiment. So even this very simple approximation is not completely useless. Nevertheless, it's not always accurate enough. And the next class is known as the generalized gradient approximation, where we say, okay, since this is not a uniform electron gas, let's add some information, at least from the immediate vicinity, by adding a gradient term, which somehow takes into account also variations. And people have been working on that for many years. And it really does improve things. For example, it improves the quantitative accuracy of calculations of quantities like atomic energies. It improves overbinding that is typically found in LDA. And it improves the overemphasis of packed structure that LDA usually does. But it doesn't change qualitatively over LDA. It's about the same, it's just quantitatively more accurate, which is a good thing. Now, beyond LDA and GGA, which I just discussed, a major class of functionals is hybrid functionals, which will actually be at the center of my talk today. So what is a hybrid functional? In a hybrid functional, we incorporate a fraction of exact exchange. What is exact exchange? It's the exact expression for exchange from Hartree-Fock theory. And that is the precise way of taking into account the Pauli exclusion principle, or equivalently, the anti-symmetrization of the wave function. So if this is the exact exchange, why take only a part of it? Why not take all of it and be exact on the exchange? That's because we don't have good expressions for correlation. And actually keeping some approximate exchange helps balance the computation of exchange and the computation of correlation such that their overall result is still useful quantitatively. I will have much more to say about this as I go along. Right now, I'm just introducing the exact exchange expression. One thing to notice about it, and this will become important later, is that you see that it now depends explicitly on the orbitals. It's not just a functional of the density, so we will have to do something about that, and we will talk about that in a few minutes. One more thing that I want to mention is that almost all standard functionals, be they LDA or GGA or various types of hybrids, which are the various acronyms that you see here, don't do very well when it comes to dispersive interactions. So for example, hydrogen bonds and van der Waals interactions. What you see here is a benchmark study that we did a few years ago with a group of Alex Tkachenko, who is now in Luxembourg. And basically, we calculated the mean error with respect to very accurate coupled cluster calculations for the so-called S22 set, which is a set of 22 weakly bound complexes, which is divided into hydrogen bonded complexes, van der Waals bonded complexes, mixed and overall. And basically, all functionals do quite badly unless we add dispersive corrections. So basically, pairwise interactions that are non-empirical between each pair of atoms. And then we can actually get very good accuracy. So this was already a while ago. Now there are even more accurate methods. I won't go into that, but I do want to point out that with one way or another of dealing with dispersive interactions, we can also deal with weak chemical interactions, and that's very important. So based on what I showed you so far, we can already do a lot of useful things. For example, let me show you some recent examples from my work, or from the work of my group rather. So for example, this is the work of my PhD student, Anna Hirsch, who already graduated. So together with experimental groups, we looked at the eyes of crustaceans, such as this prawn here or this lobster here. And it turns out that their eyes are actually made entirely out of mirrors. There are no lenses in there at all. It's all reflection. And those mirrors are actually a molecular solid that is comprised from this molecule isoxanthopterin that you see here. So the question that the experimentalists ask is the following. They said, look, we take an X-ray diffraction spectrum of the crystal. This is what you see here in purple and in green. And we see that it's crystalline because we get diffraction peaks. But the sample is too small and not ordered enough. We can't really solve the structure. So can you do that on the computer? So we played around with various structures on the computer based on essentially crystallographic information and a simple idea that says that we want to maximize hydrogen bonding. So we did that together with a wonderful crystallographer, Leslie Lazarowicz. And finally, we were able to come up with this planar structure. So this material is really completely like graphite in the sense that it is made of individual 2D sheets. The difference from something like a graphene sheet is that each sheet is not only covalently bonded, but also hydrogen bonded between the molecules. And the black line here is the simulated diffraction pattern that we obtained from this hypothetical crystal. And as you see, it's in great agreement with experiment. We could also tell why it's a good idea to have mirrors based on this. We could calculate the index of refraction, find that it's really, really high, almost 2. So it would promote total internal reflection, which is exactly what is necessary for a good reflecting mirror. The experimentalists then synthesized this material in the lab. They found that it has a different structure, and they asked us if we can find this different structure as well. And we told them that, in fact, we already did. When we were optimizing the first structure, we also found another one that is more of a zigzag ribbon structure. And that one agreed really well with the diffraction pattern for synthetic structure, but it's not as good as a mirror. It's still a very good mirror, but it's no longer a great mirror. So we could make really here 2 predictions for the structure, both of which were confirmed. As another example, we can also look at properties beyond structure. I already showed you an index of refraction, but here's another example. We can look at mechanical properties. For example, here, working with a group of Udi Gazit at Tel Aviv University, we could look at basically kind of a synthetic DNA-like structure, or based on guanine, which is called FMOC guanine. So it's a conjugated peptide nucleic acid crystal. You can see one view of the structure here. And the experimentalists could measure the Young modulus, find that it's reasonably high. It's in the tens of gigapascal. And in this little table here, you can see a comparison between experiment and theory for the minimum value, the maximum value, and the average value. All of them agree very well between theory and experiment. So there's also the prediction here that there's anisotropy in the crystal. Some directions are stiffer than others, which is confirmed. One final example I would like to share here, again from the work of Anna Hirsch and Ido Azuri, is we looked at brushite. Brushite is a hybrid organic-inorganic mineral. It's a calcium phosphate, but there are also water molecules inside the unit cell, not as a solvent, but actually a molecule that is part of the unit cell. This mineral is interesting because it's responsible for about 20% of all kidney and bladder stones. And you can see an example of a bladder stone from an actual patient here, something that you really don't want to have, but it happens. In any case, people, as part of trying to understand this material, have tried to look at its infrared spectrum. On the bottom in blue is the experimental spectrum. As you can see, it's pretty rich in detail. And so there was some controversy in the literature about how to actually assign the various peaks here. 4 different groups measured that, and they all essentially agreed that this is what the spectrum looks like, but they had differing views on how to interpret the spectrum, especially when it came to the contribution of the water molecules. And here you can see that on the computer, we could have a simulated spectrum. That's the black one, which is in great agreement with the experimental one, even in this region where there are really many, many features. And so we could really assign individually where each feature is coming from. So these are just a few highlights to show you that even relatively simple flavors of approximate density functional theory are already enough to get to quantitative agreement with experiment and help us in interpreting or even predicting various phenomena of interest when it comes to structure, mechanical properties, electrical properties, optical properties. We also have examples involving magnetic properties that I will not show you today for lack of time. So really a broad range of applications. However, and this is what I'd like to focus my talk on, there are also issues that don't quite work so well with DFT in the standard functionals. One particularly bothersome feature is that we would have loved to look at the HOMO energy level and the LUMO energy level, so the highest occupied energy and the lowest unoccupied energy, and say that the difference between them is just the fundamental gap, so the difference between the ionization potential and the electron affinity, or in other words, the difference between how much energy it takes to liberate an electron and how much energy you can gain from adding an electron to the material. So this is very intuitive and sounds reasonable, but sadly, it's not true. There have been two papers already back in 1983 that showed that even if we had the exact functional, then the HOMO-LUMO gap is not the same as the fundamental gap because they differ by some quantity known as the derivative discontinuity, delta XC, that I will explain more about in a slide, in a couple of slides. So that has been confirmed numerically since by many calculations, and it's a most unfortunate conclusion because it means that Kohn-Sham eigenvalues do not mimic the quasi-particle picture even in principle, and therefore most people, instead of relying on DFT for quantities like that, they turn to many-body perturbation theory based just on DFT as a starting point, and then going to a much heavier calculational machinery, also more difficult theoretically, and then they could do it, but these are very expensive calculations. And I'll have more to say about that in a moment. Another interesting problem is the charge transfer excitation problem. Obviously, in nature, exciting charge from one place to a physically different place is very important for processes like photovoltaics, like some issues in photocatalysis, certainly for photosynthesis. So clearly of very much importance. And nevertheless, if you calculate charge transfer excitation energies, the result is usually quite poor. So first I should say that in general, DFT that I have explained so far is a ground state theory. To look at optical excitations, one needs to look at an extension of the theory known as time-dependent density functional theory, which basically starts from the time-dependent Schrödinger equation instead of the time-independent one. Then it's possible. And it actually works quite well for simple excitations. But for charge transfer excitations, it's rather poor. And you can see it here. This was first pointed out by David Tozer, again, more than 20 years ago. Here's a dipeptide. So the lowest excitation from one unit to the other with a wave function method is supposed to be almost 8 electron volts in energy. Time-dependent GGA mistakenly thinks that it's only 4.5. So a very serious underestimate, which can have very serious consequences. Here's another problem. So when it comes to solids, this example is silicon, obviously a material of great practical importance. So not only is the band gap wrong, we already said that, the band gap is only a little more than half of what it should be, but also the optical absorption spectrum is wrong. So what you see here in orange is many-body perturbation theory. It's known as GW plus BSE, never mind beta-saltpeter equation. That's not so important. The important thing is that it's a more precise wave function-based method. So that's our reference. If we do time-dependent DFT with PBE, which is a type of a GGA, you see that not only is the onset of absorption wrong, we can maybe live with that because we know the gap is wrong, but the entire line shape here is wrong. So the entire prediction for the optical absorption spectrum is actually bad, and we should do something about that. And a final example is that in molecular solids, there is a phenomenon known as gap renormalization, which means that the gap of the crystal is much smaller than the gap of the molecule. This is shown here for 3 different molecule crystal combinations: benzene, pentacene, and C60. So for all of them, this is the molecular gap as calculated by GW, so many-body perturbation theory again. And you see that the gap of the solid is much smaller. This is correct, and this is not coming from orbital hybridization because this is a very weakly bound solid. It's just van der Waals interaction, so there's very little orbital hybridization. What's really going on is a dielectric response. As I try to pull out an electron from one of these materials, from one of these molecules, all the surrounding molecules polarize in response to the charge that I have there now, and then basically create an image charge, and that decreases the ionization potential, increases the electron affinity because it's of opposite sign, and in the end closes the gap. And you can see that it's a very large effect. For pentacene, for example, the molecular gap is about 5 electron volts, which would have made it useless as an organic semiconductor. In the solid state, it's only 2.5 electron volts or so, which make it a good organic semiconductor. So this is a known effect captured very well by GW. But if I look at the same with PBE, I see nothing. And if I say, okay, I'll take a hybrid functional with some Fock exchange, like I explained before, these are two different flavors of hybrid functional, still nothing. So basically, here's another failure of standard DFT, that this gap renormalization phenomenon is completely missed. So now, the thrust of my talk is that we have been thinking about these things for a very long time. And ultimately, we realized that all of these apparently completely different failures have common origins. And therefore, one can come up with a unified approach to solve all of them within one framework. And this rests on 3 general ideas. One is generalized Kohn-Sham theory. The other is an exact asymptotic potential. And the third is the ionization potential theorem. And I will explain what all these 3 are as I go along. And I will show how they solve all of the problems that we now introduced. Okay, so a crucial concept to understand where all of this is coming from is what's known as piecewise linearity in DFT, which was introduced in this landmark paper from Purdue, Parlev, and Baldus back in 1982. So what's the idea here? The idea here is how would the energy change as a function of the number of electrons if the number of electrons is allowed to be fractional. Now you could ask yourself, well, what does it even mean, a fractional number of electrons? What's the point of having 3 1/4 electrons? There's no such chemistry, right? So the idea here basically is that this is an ensemble state. So basically, if I'm saying that I have 3 1/4 electrons, it means that my system is in touch with some electron bath, and it will have 3 electrons 75% of the time, and 4 electrons 25% of the time. So it's a classical probabilistic combination of quantum systems that's known as an ensemble state. And then the energy is just a simple linear combination of the 2 different pure states with the integer number of electrons. And that means that the energy as a function of the number of electrons is just a sequence of straight lines. So far, that's pretty simple. There is also a proof for that that doesn't involve ensemble arguments that I will not go into, but there are references down here if you're interested. The important thing is that then there is also a theorem due to Janak that says that the derivative of the energy with respect to the occupation of the orbital is actually the eigenvalue. So that means that the highest eigenvalue is just the derivative of the energy with respect to the density, which is just the slope here. So the highest eigenvalue is a set of is like a staircase plot as a function of the number of electrons. And most importantly, the HOMO energy in the exact functional should be just the slope here. And the slope here is just how much energy it costs me to take out an electron. So that means, and that's the ionization potential theorem, that the highest occupied eigenvalue in the exact functional should be exactly minus the ionization potential energy. And again, this is an exact result. It's not an approximate result. So that's one thing that we will use later. The other thing is that you see that because of this piecewise linear character, every time I hit an integer number of particles, there should be a jump in the slope here. So there's one slope, and then all of a sudden there's another slope. So there's a derivative discontinuity. That's okay. It's completely physical. It's not something very mysterious. It just reflects the fact that the energy needed to remove an electron and the energy needed to add an electron are not the same. At the same time, if I look at it from a Kohn-Sham perspective, Kohn-Sham equation perspective, something should be able to provide this discontinuity. Now, most potentials in the equation cannot do that because they are continuous functionals of the density. So the only thing that can cause this is A, the kinetic energy, and B, the exchange correlation potential. So the exchange correlation potential must jump by a constant. And if we go back to where we had the equation, right here, so this guy jumps by a constant as I go across an integer number of particles. This constant is known as the derivative discontinuity, delta xc, which I showed here. So then that's the problem. The problem is that minus epsilon HOMO really is the ionization potential, but epsilon LUMO is not the electron affinity because it's missing this derivative discontinuity. And that's why the gap comes out to be incorrect in principle. Okay, so how do we work with it? So now comes the second ingredient, and that's generalized Kohn-Sham theory. Remember that I already told you a few minutes ago that hybrid functionals mix Fock exchange with Kohn-Sham exchange. And because Fock exchange is orbital dependent, the way that this is usually done is with this Fock potential, same as in Hartree-Fock theory. So there's a fraction A of Fock exchange and a complementary fraction Y minus A of typically GGA exchange. So the GGA exchange is just a multiplicative potential like before, everything is fine. But the Fock exchange is actually a non-local integral operator. So you could say, well, so what? Well, the problem is that this really places it outside Kohn-Sham theory because Kohn-Sham theory, the entire proof of the theory, relies only on multiplicative potentials. So for a while, when hybrid functionals were first introduced in the early 90s, chemists liked them right away because they resulted in improved accuracy. But physicists initially hated them because they felt that it's a theoretically unallowed thing to do. You take something that is non-local, you stick it in a local picture, and you don't know what you're doing and why it works. Well, it turns out that there's a very good reason for why this is allowed. And this was first explained in this landmark paper by Zaidel et al. In 1996. And that is that hybrid functionals really are outside Kohn-Sham theory, but they are well within generalized Kohn-Sham theory, which basically, instead of mapping into a non-interacting electron picture like before, maps into a partially interacting picture that is still represented by one Slater determinant, so one can still have an orbital picture. That's a bit of an abstract mathematical argument, so if you didn't follow it all the way through, that's okay. The important thing for our purposes is that now there's more than one exact map, because it depends which partial interaction I'm using, which depends on how much Fock exchange I'm taking. So I should choose the one that I like. Which one will I like? I would like to choose one that minimizes this derivative discontinuity problem. What do I mean by that? Remember that before I said that only the kinetic energy and the exchange correlation potential can offer a way to overcome this derivative discontinuity. But now there is also this Fock exchange. There is another integral that depends on orbitals. So that too can exhibit a discontinuity. So maybe I can push all of the discontinuity here, then nothing will have to jump. And then if the exchange correlation potential doesn't have to jump, then actually this will be zero, and I will be able to identify the gap with a HOMO-LUMO energy. So how do we do that? So we do that with the help of what's known as a range-separated hybrid function. What's a range-separated hybrid functional? This is a concept due to Andreas Savy. And the basic idea is very simple. We take the 1 over r Coulomb repulsion, and with the help of, for example, the error function, we divide it into a long-range term, error function, and the short-range term with a complementary error function, which is just 1 minus the error function. So this term only exists for large r, this term only exists for small r. And together they are the exact Coulomb repulsion. Now, as it stands, this is a trivial mathematical identity and it doesn't seem very interesting. But we can treat those two ranges now differently. In the long range, we want to emphasize Fock exchange. Why? Because that takes us back to our third principle. We want to have the exact asymptotic potential, which is 1 over r. And that only comes to be if we have full Fock exchange. Why do we want the full asymptotic potential? Because if we're going to properly describe properties where we take an electron out of the system into infinity or bring in an electron from infinity back to our system, we need to have the asymptotic potential correctly, because that's the barrier that the electron feels in order to leave the system. So we treat this term with Fock exchange, we treat this term with a GGA exchange, and then we have a range-separated hybrid functional that has the correct asymptotic potential, but still balances exchange and correlation well. The remaining issue then is how to choose this parameter gamma here. Gamma is known as the range separation parameter, and that's really the same as asking, so okay, I will divide into long range and short range, fine. But what's long range? What's short range? What do I think of as far and what do I think of as near? How do I know that? So in the early range-separated hybrid functional literature, people did that semi-empirically, for example, in these papers right here, by fitting into some data set. We didn't want to do that for two reasons. First, we didn't want to introduce empiricism. And second, as I will show you in a moment, it's still not good enough for a spectroscopy. So what we did instead, and that is work that was started with my friend Roy Baer at the Hebrew University and his student Tamar Stein, who was working with both of us, and is now herself a faculty member at the Hebrew University. And that is to bring back our old friend, the ionization potential theorem that I told you about a few minutes ago. Remember that I told you that in the exact functional, minus epsilon homo is the total energy differences between cation and neutral, so the ionization potential energy. Well, for each choice of gamma that I would make, I can calculate the left-hand side, and I can calculate the right-hand side, and I can ask myself whether they're the same or not. And I can look for gamma such that it is the same. If I found it, I'm happy, that's my winner. Now, there's no such theorem for the electron affinity, but I can do the same for the anion. So saying that epsilon homo of the anion is the total energy difference between anion and neutral. So then I would have a condition that effectively talks about the electron affinity, because the ionization potential of the anion is the same as the electron affinity of the neutron. So I have two conditions, only one variable, and I will minimize it, say, in the least square sense. Now, the point that I cannot emphasize enough is that this means that we are tuning the range separation parameter per system, but we are not fitting anything. We are not fitting to experiment. We are not fitting to a different form of theory. We are only asking that an exact condition within DFT be obeyed. How does that work in practice? So here's a simple molecule, H2TPP. There's nothing special about this molecule. It's just a convenient test case, that's all. So here is the first condition, epsilon homo plus IP. If this sum is 0, then the condition is obeyed. And here it is as a function of gamma. That's the red curve here. And you see that it goes down to 0 at some point. Here's the second condition for the anion. So epsilon homo of the anion plus the ionization potential of the anion. Again, if it's 0, the condition is obeyed. And now you can see there's sum of absolutes in this case, which is the blue curve. And you see that there is definitely a value that minimizes it. We call this the optimal range separation parameter. And we call this procedure an optimal tuning of the range separated hybrid functional. And if we do that, this is the parameter that we're now going to use throughout. So what do we gain if we do that? So for this molecule, we chose it because there are good experimental reference data. This is the ionization potential in the gas phase. This is the electron affinity in the gas phase, 1.7. And this is the optical gap, so minimum energy to excite optically an electron to create a singlet excitation. These are well reproduced by many body perturbation theory. But you see that with GGA or even with a conventional hybrid like B3-LIP, the gap is terrible. It's a great underestimate of the actual gap. The actual gap is almost 5 electron volts. GGA thinks that it's less than 2. B3-LIP thinks that it's less than 3. But our approach with optimal tuning gets everything right. The gap is correct, the fundamental gap is correct. The optical gap, which is much smaller due to electron-hole interaction, is also correct. And basically, we have the exact same picture as in many body perturbation theory for a much lower cost. Now, this, of course, is one molecule. So together with my friend Jeff Neaton at Berkeley, and this was a a study led by Sivan Rafaeli Abramson, who was my student and is now, again, with her own group at the Weizmann Institute, and Isaac Tambling, who was a postdoc with Jeff and now has his own group in Canada. So we looked at the entire set of 148 molecule that's known as the G2 set. That's actually the set that was used to fit B3-LIP. So we're giving B3-LIP the home advantage, so to speak. And nevertheless, we plot minus epsilon as a function of the experimental ionization energy. We see that for all 148 molecules, without a single exception, we are well on the line here. So theory equals experiment exactly is y equals x. So where you want to be is on the line. And you can see that B3-LIP is seriously and systematically off the line. So it's a significant improvement. Now you can ask, okay, what else is it good for? Well, it's particularly useful for charge transfer excitation energies, which is in fact what got us thinking about this in the first place. So to understand why, let's think about the Molekin limit. Molekin, already in the early 50s, said, well, suppose you have a donor that is very well separated from an acceptor. What would be the minimum energy to excite an electron from the donor to the acceptor? Well, I'm going to have to pay the ionization potential of the donor to get the electron out of there. I'm going to gain some of that energy back in the form of the electron affinity of the acceptor because the electron gains that energy going on the acceptor. And then there is also a stabilizing 1/r term, which is just the Coulomb attraction between the electron that is now in the acceptor and the hole that is left behind on the donor. Fine. Problem is that if I do a linear response time-dependent DFT in the same limit of a well-separated donor and acceptor, then after some math, which I'm not showing here, the following result emerges, that time-dependent DFT thinks the answer should be epsilon homo of the donor minus epsilon lumo of the acceptor, and if it's a hybrid functional, then minus A/R, where A is the fraction of Fock exchange. So in a GGA, A is 0, so this term would not appear. Okay, now here's the problem. In a standard functional, I already showed you that the ionization potential is not epsilon homo, say in a GGA or in a hybrid. The electron affinity is not epsilon lumo, and A is not 1. In GGA, it's 0. In something like B3-LIP, it's 20%. So every single term here is actually wrong. So there's no surprise that the results come out badly. Now, I hope I have convinced you that in our approach, on the contrary, epsilon homo is the ionization potential, epsilon lumo is the electron affinity, and A asymptotically is 1 because we constructed the functional this way. So this must work. And indeed it does. And what we did is we took some gas phase data from the literature from the group of Hanazaki at Tokyo University, very nice experimental paper. They took systems involving very simple donors, so benzene, toluene, etc., and an acceptor that is TCNE, tetracyanoethylene. These are their experimental results in green here. Now you see again, if I do time-dependent GGA, awful results. Underestimate true excitation energies by more than 2 electron volts. Terrible. If I do time-dependent B3-LIP, which is normally the go-to functional in simple organic chemistry, and these are simple molecules, it's almost not any better. If I do a range-separated hybrid functional, in this case something known as BNL, the result is better, but I still have a very serious overestimate with a default parameter. But if I optimally tune in the way that I just explained, then actually I have full quantitative agreement with experiment. And only after we have done that, the many-body perturbation theory people wanted to see if they could do it too. Initially, it wasn't very good, and only later it was shown that they can do it too, but they have to use a trick known as partial self-consistency that I will not talk about. It makes the calculation even more expensive. So we can get the right answer for the right reason in a much easier way. The nice thing also is that this doesn't come at the price of dealing with regular excitation. So the group of Johann Auersbach took 40 pi conjugated dyes, calculated the valence excitations for all of them, and found out that not only does our approach do well for those, in fact, it does better than anything else that they tested. So this is nice because it's really someone else objectively evaluating our work, and they came to a similar conclusion. We had a similar conclusion on a more limited set of molecules earlier in this paper that you see down at the bottom of the slide. Okay. So just a quick word on the formality. I already showed you that DFT is basically underlined theoretically by the Kohn and Shem equation from 1965. This has been extended to the time-dependent domain by Runge and Gross in 1984. I also mentioned that one can go from Kohn-Shem to generalized Kohn-Shem to non-multiplicative operators, as shown by Zeidel et al. In 1996. But then at some point, we realized that nobody showed that you can also do the same for time-dependent DFT. So people have been doing time-dependent DFT with hybrid functionals for a while now, including the example that I just showed you, but nobody showed that it's allowed. So finally, Roy Baer and I did that in a special issue in honor of Professor Gross that came up with the original proof. And I think that's important to have a fundamental theory that allows this. Now, I'm definitely not saying that this paper here in red is as important as the 3 blue papers. On the contrary, I'm saying that it isn't, because the 3 blue papers, each of them had a drastically new idea, whereas this work just synthesizes these 3 existing ideas. But still, it's good to know that when you do a hybrid functional calculation in time-dependent DFT, that you're actually allowed to do that. Okay, now back to the normalization story. So I already showed you how to get molecular gaps. I already showed you that we can solve the charge transfer problem, but I still didn't show you whether we can also solve the renormalization problem. So actually, the key to that is to understand that it's really a dielectric response. I already showed you that standard functionals fail. And in fact, what I just showed you also fails. It gets the molecular gap correctly, but it still doesn't show the renormalization. Why? Why is what we did so far not enough? Well, remember that there has to be a dielectric response here, that the dielectric response is what governs this effect. Now, in a dielectric material, because of screening, the asymptotic potential is no longer 1 over R. It's actually 1 over epsilon R, where epsilon is the dielectric constant. That's something that we know from basic electrostatics. So that should somehow be in the functional. So how do we do that? So again, we return to this range partition scheme, the error function and the complementary error function. And now we further divide it in the short range by alpha and 1 minus alpha, in the long range by 1 over epsilon and 1 minus 1 over epsilon. Now the terms in this pink frame here, those we treat with Fock exchange. So that means that we have some Fock exchange in the short range, so we have something that behaves like a good hybrid functional, but also in the long range, we have the correct asymptotic 1 over epsilon dependence. And then the complementary fractions, the gray frame here, that's treated by GGA as before. So that's known as a screened range separated hybrid functional, because now the asymptotic potential is 1 over epsilon. And then, and this is work that Sivan pursued with Sahar Sharifzadeh and again with Jeff Nita, you see that now we do have this renormalization. Look at pentacene, for example. Here is the molecular gap on the left. Here is the solid state gap on the right. So first of all, the normalization is obtained just by going from epsilon equals 1 to epsilon being its true value as calculated from the crystal. Not only that, the solid state result is as accurate as GW in good agreement with experiment. And the molecular result is actually more accurate in this particular flavor of GW. So not only do we solve the problem that the molecular gaps are too small, we also solve the problem that there is no renormalization. And if we do that, if we take a fraction of Fock exchange also in the short range, we can actually get more than the gap. We can get the entire photoemission spectrum of a crystal. This example has to do with quinacridone, which is an air-stable derivative of pentacene, which you can see the molecule right here. These are experimental photoemission data measured in the group of Mike Ramsey in Austria. And you can see here that we have a problem that if you do PBE, which is a GGA functional, the result is so bad that then even if you do GW on top of it, the agreement with experiment is still quite poor. That has to do with what's known as a self-interaction error. Some of the orbitals in these molecules are fairly localized on these substitutional groups. And GGA does a very poor job in describing localized orbitals because it mistakenly assigns some repulsion of the electron from itself, which is obviously not physical. This effect is mitigated by Fock exchange, which basically doesn't let the electron go near itself, so to speak. And you can see with it with a screened range separated hybrid, which is the red line here, we can get a much better agreement with experiment. And we can really see that this is the main reason for that, because if we put in alpha equals 0, which would make it like a GGA in the short range, we can actually reproduce the bad GGA result. Normally, of course, there's absolutely no reason to reproduce a bad result, but it shows that this is really the underlying cause. And then when we have full agreement between theory and experiment, then of course we can look at the individual orbitals and we can fully assign what's behind each peak in the photo emission curve, so we can get a really complete understanding of the electronic structure of the underlying molecule and the underlying crystal. Okay, one more thing that I will not dwell on in detail, but I will just say that one can even combine this optimal tuning with a screened range separated hybrid with a polarizable continuum model, which is basically a dielectric medium that encompasses a molecule residing in a cavity. And then you don't even have to calculate the full crystal. You can just put a single molecule inside this dielectric medium and still get the correct solid state band gaps, which we showed here in this work with Barry Dunitz's group. And more importantly, perhaps get solid state interface charge transfer excitations correctly, which is work that we've done with a group of Jean-Luc Breda. I will not show this for lack of time. I have backup slides. You can ask me about it later in the questions and answers if you like. But I will also mention that we have an entire overview article that I wrote with my good friend Stefan Kuman from Bayreuth University that discusses how exactly to combine optimal tuning with PCM and what are caveats and how to do this correctly. So in the last few minutes that I have, I just want to focus on one more important thing. And that is that I showed you how to get band gaps for a molecule, or well, not band gaps, gaps for a molecule, but more important perhaps is how to get band gaps for a solid. And here we do have a problem. Why? Because, you know, if we calculate a solid, we have many periods of the same unit cell. The wave function delocalizes, and one can show, in fact, Wei-Tao Yang's group has shown that back in 2008, that in the limit of a very large solid, this ionization potential theorem issue is obeyed trivially. In other words, no matter which functional we take for a really large system, because of orbital delocalization, epsilon homo would always be minus the ionization potential. So now you could think, hey, that's a good thing. The condition is always obeyed, great. But for us, that's actually a really bad thing, because if the condition is always obeyed, regardless of whether the result is good, then we have no reason to prefer one range separation parameter over another, and we cannot choose the one that produces a good gap. And here is an example of a typical bulk solid. So this delta I, the deviation from the ionization potential theorem, is 0 all the time, but the gap keeps changing if I change the range separation parameter. So there's no reason to prefer one value over another. So first we checked if there are any conditions in which the conclusion from Wei-Tao Yang's group can be violated. The answer is no. So we came up with 2 other papers that basically have 2 different alternative proofs of the original proof by Yang. So now you have 3 different proofs for the same thing, but the bottom line is still the same. It's not helpful. So what did we do instead? First, we wanted to see, well, is it even worth doing? So we took a non-molecular solid, in this case, lithium fluoride. And we said, well, suppose we choose the range separation parameter empirically as a start, just to see that we get the right gap that is known experimentally, and calculate the optical spectrum. Do we gain something from it? The answer is absolutely. And in fact, it's a very strong example, because you see experimentally, and that's the blue line down here, this material has a very sharp excitonic peak at 12 point something electron volts. This sharp excitonic peak is confirmed by many body perturbation theory. Again, accurate but expensive. That's the red curve. But if I do time-dependent LDA or GGA, you see that actually I have this gray line here, which looks nothing like experiment. Agreement with experiment is basically non-existent. The absorption starts way too early and the exciton peak is gone and it's just a mess. So with our time-dependent screened range-separated hybrid approach, which is the black line, you see that full agreement with experiment is restored. And later, David Wing, who recently graduated from my group, together with Jonah Haber, a student in Jeff Neaton's group, repeated this for a wide range of semiconductors and found that it works throughout. This example is aluminum antimonide. And you can see that even for this complicated material, which has 3 peaks of absorption because the first peak is split because of spin-orbit interactions, there's still great agreement with both experiment and many body perturbation theory. So this is worth doing. So how will we get then rid of this empirical parameter? Because remember that in this slide, the work of David and Jonah, and also in the previous slide, we still have one empirical parameter. We still fit the gap. We don't want to fit the gap. We want to predict the gap. So how are we going to do that? So this is our very recent work done by David with Guy Ohad, a newer student in the group. The idea is, well, if the problem comes about because the wave function is delocalized, then let's localize it again. One can always localize a wave function with the help of what's known as a one-year function, which basically takes a set of molecular orbitals and turns them into local orbitals. For example, for silicon, the one-year transformation ends up showing you the covalent density that really binds 2 atoms together in each of the tetrahedral bonds of the silicon lattice. So now the idea is, okay, so let's not remove the electron from the valence band wave function. Let's remove the electron from the one-year orbital. That can be done since the one-year orbital is not an eigenstate of the Kohn-Sham equation. We need to force it. So we need to add a constraint so that the electron can go out of there. This can be done. In fact, Ma and Wang showed how to do that a few years ago. And then we use the following ansatz. We say that, well, we have, which is again due to Ma and Wang, we have the same idea as in the ionization potential theorem. So we will calculate the total energy differences now with the constraint that forces us to pull the electron out of the one-year orbital. And instead of the HOMO eigenvalue, we'll just use the expectation value of this of this one-year orbital because it's not an eigenstate, so it's replaced by an expectation value. Bottom line, even if you didn't follow all of the mathematical details, it's the equivalent of the ionization potential theorem in this more involved case. Now, definitely, again, we plot deviation from the ionization potential theorem as a function of the range separation parameter. Now there is deviation. So now there is an optimal parameter. So this is the one that we will choose. And we did that for a very large set of semiconductors and insulators, starting with a really tiny gap of 0.2 electron volts indium antimonide and going all the way back to lithium fluoride, which is 15 electron volts. So really a huge range with everything in between, other semiconductors like silicon, gallium arsenide, indium phosphide, and other insulators, magnesium oxide, aluminum nitride, etc. And throughout all of this process, again, this is theory. We call this one-year optimal tuning of a screened range separated hybrid, a lot of letters, but that's what it means. So this is theory, this is experiment. And as you can see, there's a great experiment between theory, there's great agreement, between theory and experiment throughout, with the largest error being only 0.2 electron volts and the mean error being 0.1 electron volts, which is again, not only as good as standard many body perturbation theory, but in fact better. So I'm almost at the end of my talk. I'd just like to point out 2 things. First, like any approach, our approach also has limitations. So far, I talked about some of the success stories, and I think there is enough success to make this useful, and many groups indeed are using it. But there are also issues. 2 specific issues are what happens in systems with strong heterogeneity. So for example, a molecule-metal interface. So then it turns out that the parameters for dealing with the molecule are quite different from those for the metal. So that requires, more specialized approaches, which are not yet completely general, but we do have some publications on this issue. And the other issue is what to do when we have strong correlation. So far we talked about the exchange, but if there's also very strong correlation, then again, we need to go beyond what I just showed, and we have some preliminary work on that as well, which are these references down here. So that brings me to my conclusion slide. As I showed you, the standard way of thinking in time-dependent TFT or DFT is that it cannot quantitatively predict issues such as molecular gaps and solid-state band gaps, gap renormalization of molecular solids, band structure and excitonic line shapes in solids, charge transfer excitation energies, photo emission spectra, and much, much more. The consensus is that none of this works in DFT. Now, the road is still long, and I just pointed out some of the remaining difficulties, but nevertheless, hopefully what I have shown you in the last 45 minutes or so is that we can remove the knot. Time-dependent DFT actually can quantitatively predict all of these things with the help of screened range-separated hybrids that are optimally tuned. So with this, I will stop. I will thank you very much for your attention, and I'll be happy to take questions if you have them.
Okay. Wonderful talk. So
thank you very much.
Before we yeah. So before we collect the question from the audience, can I ask several questions? Because I have heard you talk, when I was in Weizmann, and still, since I'm not a theoretician, it's still not very easy to follow. So there are several technical questions. For example, the one that if you go back to the slide where you show the using the B3LYP hybrid, the functional, the calculation of ionization and the
this one?
No, the previous one.
This one?
No, I think no, previous one. Yeah, this probably this one. No, let me see. Yeah, yes, this one.
This
okay.
One? Okay. Mm-hmm.
Yeah. No, the 22nd. The 22nd.
Okay.
Yeah, this one. So this slide show that the B3LYP is really not good in predicting the ionization potential and electron affinity, right?
Right, from the eigenvalues. So what you see here are the eigenvalues. So epsilon HOMO of B3-LYP is not a good indicator of the ionization potential. Epsilon LUMO is not a good indicator of the electron affinity. If you do total energy differences, B3-LYP is actually better than that. And then it becomes reasonable. But total energy differences will not help you if you're trying to do things like the charge transfer problem that I showed a few slides after that, like this. Because here you really need the eigenvalues. So the fact that the eigenvalues are wrong, if all you need is the ionization potential of the molecule, you can get around it by total energy differences. But if you're going to need also charge transfer excitation energies, for example, or other properties, you'll really be in a problem. Then there is nothing that B3-LYP can do to help you. And you really need these more approaches.
Okay, got it. That's the question I have. Okay, so I guess some question from the audience. Let's see, I'm not quite sure I understand this question. This question asks, the OTSRSH method is applicable to all type of hybridized functional?
Okay. So as I understand the question, does it have to be used with a range separate? Well, I can divide the question maybe into two parts. First question is it restricted to a specific type of range separated hybrid, or can it be used with any range separated hybrid? So the answer is any range-separated hybrid that is asymptotically correct will do. Over the years, for various reasons, we have combined it with BNL, with LC omega PB0, with omega B97X. It works equally well with all of them. The second part of the question, I think, as I understand it, is, well, do I have to use a range-separated hybrid functional at all? Or maybe I can, in a similar way, optimally tune V3 lip, just optimally tuning the fraction of exact exchange in V3 lip. So here I would say, no, it's not a good idea to do that. There are a few papers that did that and they got specific properties correctly. So this is not criticism, but generally it's not a good idea because the functional is not asymptotically correct. When you try to optimally tune a functional that is not asymptotically correct, you end up with a truly huge fraction of exact exchange because somehow the functional has to compensate for what's missing. So for example, if you optimally tune something like B3 lip, typically you see that the prediction is that you need something like 80% of exact exchange to get the ionization potential theorem correctly. Now then, okay, you got the ionization potential theorem correctly because you insisted on it, fine. But we know that with 80%, bond lengths and thermochemistry and energetics, all that is going to be awful. There's a reason in the end why we typically use 20% and not 80%. So optimal tuning, in my view, is a good idea only if combined with a functional that is asymptotically correct, and that would be a range-separated hybrid for a molecular state or a screened range-separated hybrid for the solid state.
Okay. Let's see. Some audience ask the homo-LUMO gap, whether it will be smaller in the LB film.
Well, yes, in general, yes. So if I look at a two-dimensional array of molecules, whether it's an LB film or a self-assembled monolayer or anything like that, one moment, I want to go back to this slide, yeah. So now you don't have a three-dimensional crystal, but you do have a two-dimensional array of molecules, which means that as I try to excite out of one molecule, I will still have the electric response from all of its neighbors. So it will not be as large an effect as this because I only have a two-dimensional dielectric response and not a fully three-dimensional dielectric response. But yes, as soon as there is some dielectric response, then there is some renormalization because there is some image charge. So yes, the gap will be reduced, not by as much as what you see here.
So how about the case of a self-assembly monitor on the surface of a metal, which is a system that we work a lot for the molecular electronics?
Right. So one second. Yeah, so I don't have it on this slideshow, unfortunately, but I will explain the general idea. So this is one issue that I quickly mentioned when I was talking about the limitations. So this is something that, in fact, we studied in these two articles here, which was a joint work of my postdoc, David Egger, and Zhenfei Liu, who was then a postdoc with Jeff and now has his own group at Wayne State University. So basically what Zhenfei and David showed is that when you have a molecule that's weakly absorbed on a metal, basically you can get around this problem by calculating the image charge from the metal. And then if the molecule is more strongly bound, you can find an equivalent, an effective dielectric constant that mimics the response from only the metal. That's the content of these two papers. So now to answer your question more directly, so if I have a self-assembled monolayer on the metal, or on a semiconductor for that matter, I now have two different sources of gap renormalization. One is from the dielectric response of the semiconductor or the image charge of the metal, and one from all of the neighboring molecules. And I need to sum up these effects correctly if I am to get the overall renormalization correctly. And that's exactly what's being discussed in these two articles here. this nanoletters in this Jacob Fizz article.
Okay. And let's see another question from the audience. This question asks, the charge transfer excitation is the singlet state excitation or not? I'm not quite sure I understand this question.
Yeah, so in this case, it is a singlet excitation because we want it to be, visible. But the calculation can, in principle, compute triplets as well. In fact, this is what I mentioned briefly during my talk. We actually calculated that. So in a solid state interface between pentacene and C60 or P3HT, PCBM, both of which are popular systems for organic photovoltaics, it's a good way to see what the screening does. So it's singlet excitation in both cases, as the question was raised. But you see that if we calculate it in the gas phase, the results are much larger than experiment. If we calculate it, in the solid state by including the electric screening, as I have shown you, then now the excitation is correct because it accounts correctly for the dielectric screening between the electron that is now on the acceptor, the C60 or the PCBM, and the hole that was left behind on the donor, the pentacene or the P3HT. So yeah, if you want to compare to experiment where you actually see an optical absorption peak, it will have to be the singlets, but the formalism can also calculate triplets. So if you want to know about the triplets, say for issues like singlet fission or for other reasons, you can definitely go ahead and do that with this set of methods.
Okay, so probably I have another question. The optimal tuning method, can it be faster? Because when you do it, you have to do like how many calculation?
So usually not so many, because by chemical intuition, we know more or less what the range, in what vicinity to look for the range separation parameter. So then all it boils down to typically is something of the order of 5 calculations. I would say 5 to 10 at most. So yeah, it's more work, obviously, but what you need to compare it to is not the single calculation, but rather a calculation at a much more computationally expensive level of theories, such as GW, or such as quantum Monte Carlo, or such as coupled cluster calculation. And then most people would be very happy to do a few DFT calculations rather than one quantum Monte Carlo calculation, say, for example, in terms of cost.
So I saw somebody is trying to use the like machine learning method to find out automatically to optimize the parameter instead of doing like the way that you doing, like to do optimization. People are trying to figure out whether we can just, based on the molecule itself, to extract the structural molecule and use this network to find out the optimized parameter. So, and probably you can make them faster. Do you think is possible?
Yeah,
I saw some of
yeah, I also saw such a paper recently. I think it's a completely valid idea, and it can be used to expedite the starting point. I would recommend that even if you have the machine learned value, to still check it, to check that the ionization potential theorem is well obeyed, and if not, then to still move a little bit. But it can certainly cut down on the number of calculations that you have to do, because it brings you very quickly to, let's say, almost the right place. So yes, I think in general that's a good idea if you can do that, and certainly it can expedite the calculation. I think that from a well-defined physical basis point of view, and also from the point of view of complete accuracy, you still want to verify that this range separation parameter indeed obeys the conditions laid out for it.
So please allow me to ask another one, because I really interested in the application of this method in the system, for example, to calculate the transport. For the calculate the transport, to use this method in the calculation of a transport problem. like the charge transport in the molecular junction, where you have to calculate the Green's function. Right? And yes. In that kind of calculation, people complain about the accuracy of the calculation. And do you think this like optimized tuned functional can work better for the
Yes. So the short answer is yes, and there are actually at least two groups that have shown that. One is that of Jean Feiliu that I already mentioned before, and the other is the group of Sui and Kwek at the University of Singapore. So both these groups have actually looked at that, and the short answer is yes. If you're interested, I can also send you specific articles later. I don't have it on this slideshow, but yes, it helps in that respect.
Okay. Let me see whether there are other questions. And some audience is asking whether there is a translator view lecture.
Whether there is what?
Whether there will be a translator view lecture, because many people have problem with the English.
Oh, okay.
Anyway, this is another question. Is asking the company whether. Okay, somebody asked, can you explain the physical significance of the G function? I don't know what that is.
Yes. Yeah. Let's go back to that. One moment. That's an important question. Okay, so let's start here. So as I said, the condition that we wish to obey is this one. In other words, the ionization potential theorem. So the way we express it is we say, instead of saying minus epsilon plus IP, this is the same as saying that we want epsilon plus IP to be 0. So minus epsilon equals IP is the same as epsilon plus IP equals 0, right? So now that's really the J. The J is epsilon plus IP. So this is our target is to make this 0 for the neutral. Our target is also to make this 0 for the anion. So then this is known as the combined target function. We want to minimize this together with this. And then this is the J that we plot here. How well have we actually done in minimizing condition number 1, red curve, condition number 2, green curve, or the total J, which is either the sum of squares, or in this case, sum of absolutes, doesn't matter so much. And that's the target function. That's the one we overall want to minimize, because then we have obeyed as best as we can both conditions. If for some reason you had the third condition, for example, you had reason to also enforce that on the cation. Sometimes it's a good idea for photo emission. I didn't go into that. And you can add the third condition here, and your J function would just then be the target of minimizing the 3 constraint. But this is basically, this J is what you want to minimize in order to get optimal tuning. If J is identically 0, then you have fulfilled the condition perfectly.
Okay. Let me see whether there are more questions. TDTMT linear. I see the audience starting like discussing about your lecture in the live broadcasting page. Okay. Let me see. There's another question. TDDFT 啥区别？这什么问题呢？ I'm not quite sure I understand this question. It seems like somebody asking the difference between TDDFT and the linear response. I don't know what that is.
Okay. Yeah. Let me clarify that. That's also an important question. So thank you for asking that. 1 second. Let me go to the relevant slide. Yeah. Okay. So let me explain what that means. So first of all, again, what is time-dependent DFT? Time-dependent DFT says that I map beginning from the time-dependent Schrodinger equation, and basically I end up with a time-dependent Kohn-Sham equation. So basically, as you might expect, instead of having, instead of having this equals E psi, you would have psi here would be a function of space and time, and instead of E psi, I would have IH bar d psi dt. Standard quantum mechanics, so that works also for the time-dependent Kohn-Sham equation. So now, when I want to calculate excitation energies, I have two ways of dealing with that. One is to really propagate the equation in time. That's possible, and people have done that, but it's expensive because I need to solve an equation not only in space, but also in time, so I need to propagate the equation. Alternatively, I can say, well, I'm only interested in the linear response. What does that mean? So I have some small small oscillating electric field, which basically mimics the incoming photon. And I just want to see the response of the system to that. So that I can do analytically, I can plug that in the equation. And basically that leads me to some kind of a matrix equation, which is known as the Casida equation, for figuring out just the response to the weak signal. And the bonus of that is that then all the time dependence is done at the pen and paper stage. And at the computer stage, I don't have to explicitly propagate anything in time because I'm really just looking for poles in the absorption of the system. And that's just a matrix equation. Nothing propagates in time. So that's what I meant. One second. That's what I meant, for example, here, when I say that it's linear response time-dependent DFT. So it's use of time-dependent DFT, but the response to the linear response to a small excitation with photons, and therefore I don't have to explicitly propagate anything in time, and it's much, 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 much cheaper than doing time-dependent DFT explicitly with actual time dependence.
Mm-hmm. Okay. Let me see. Not quite sure I understand this question. Oh, okay. Anyway, so I think that's probably all for today. So Leo, thanks again, really much. So we enjoyed the lecture very much. And also thanks for the audience for joining us this great lecture. Okay, so that's the end of today's lecture.
Thank you very much. Bye-bye.
Bye.